All right, here we're going to cover the mean value theorem, which I'm going to abbreviate as MVT. And a special case of that is going to be what we call Rolle's theorem. So let's say I have a nice smooth graph like we've seen in a previous video. And suppose I want to find the average rate of change from, let's say, x equals -6 to -2. So I would find the corresponding points on my graph, find the slope of that secant line, and I'm noticing I might be able to make a line that's parallel to this green line, but it's not secant, it's actually tangent to my graph. So here we're illustrating that the average rate of change on an interval can equal the instantaneous rate of change at a point inside that interval. So that looks to be, a little left to -4. That is in between -6 and -2. Essentially, this is what the mean value theorem says, that A rock is equal to I rock, given certain conditions. So strictly speaking, we say the mean value theorem tells us that if we have continuity on a closed interval and differentiability on the open interval, you might look at that and say, why does it need to be open? It doesn't have to be open. It just means that we don't need to have differentiability on the endpoints. We can, we just don't need it. So if those two things are true of our function, we know that we are guaranteed an x value in between a and b that makes the derivative at that x value, we'll call it c, equal to the average rate of change, f of b minus f of a, all divided by b minus a. Now, in the special case that your endpoints have the same y values, you're going to get 0, and that is something that we call Rolle's theorem, which we'll look at more in class. So this is really telling us there is a point where the instantaneous rate of change is equal to the average rate of change. This is only true if we have continuity and differentiability. So as a quick example, let's say that I have the function f of x equals x squared on the interval -2 to 1, so the closed interval, and I have to explain how MVT applies to this function on that interval, and I also need to figure out that x value that gives me a tangent line parallel to the secant line. So you can maybe take a stab at this one if you want to. If you want to pause the video and do that, I'm going to show you the solution here in 3, 2, 1. All right, so first thing, I need to specifically state the requirements. F is continuous on that closed interval. Why is that? Well, because f is a polynomial. Polynomials are continuous everywhere for all real numbers. Also, f is differentiable on the necessary interval, -2 to 1. Why is that? Well, because it's a polynomial. Polynomials are differentiable everywhere. And so, therefore, I know I can apply the mean value theorem. If I actually go ahead and apply the mean value theorem, first thing I'm going to do is find the average rate of change. So f of b minus f of a over b minus a. It looks like on this interval, I get an average rate of change of -1. So I'm trying to figure out a point on my graph where the tangent line also has a slope of -1. So to do that, I find my derivative, 2x. I set that equal to the desired slope, -1. And it turns out x equals -1/2 is going to give me a parallel tangent line to that secant line. Now you might want to do a quick double checking. -1/2 is in the interval from -2 to +1. If you got multiple x values, let's say just a hypothetical, we get -1/2 and +6. Well, I would really only take the -1/2 because that's the only one that's in that interval. Now, that's not to say that you only get one. You could get multiple x values. It just depends on the nature of your graph and how many points of tangency you have. It just really depends. Just focus on making sure you're in that given closed interval. That should do it for mean value theorem.